If you watch my last video, then you might recall this board where this ESP32 device we're using to trigger any one or any combination of these 8 outputs here, and we basically use it to trigger PAVA test messages. So it could be a test message, it could be pink noise, it could be steeper test signal. So the idea is that you can walk around the station with your, or any site basically, with your mobile phone and trigger whatever message you've set up to go to whatever zones. And you've got 8 options here basically. And that means you're not constantly going back to the comms room to turn things on and off or to make it route to a different zone or whatever. So, and the other benefit is that you're only broadcasting for the moment you're doing the test. So you could go to like the first position, do a test, stop the message instantly because you're there and you've got control, and then move to the next one, and so on and so on. So it's got some big benefits, but I felt that this board here, it's a prototype board. These pillars, if you recall, were for the LCD, which mounts on there, and then the little lead plugs in there. But on the back, look, it's spaghetti of wires, not very professional looking, and you probably wouldn't want to leave that laying on something or whatever. So I've gone to the process of getting it onto a proper PCB. So let's have a look at that now. So here's the PCB design. This is a CAD program called KiCad or KiCad, not quite sure how you pronounce it. And this is the circuit diagram. If you have a look, this is the 5-volt regulator circuit, so we can feed in 9 volts. I've set it to, but you could probably put in 12, 20, 24 volts perhaps. But the more voltage you put in, then the hotter this voltage regulator would get. We're not drawing a lot of current, so it's not a big deal, but 9 volts seems to work really well. This is the microcontroller part, and then over here are the opto isolators and the LED driver circuit basically. And then if we go to the PCB layout, so this is it in the sort of physical domain now. And you can see the footprint is 127 by 78, so that's slightly shorter than the original prototype board, but slightly longer. Now that's because on the prototype board, that this last LED here was tucked behind the LCD when you plugged it in, and I've had to push that over a bit. Now if I bring this over here, this basically a rectangle which has been sized exactly to match the LCD display. You can see if I overlay that where the studs are, you still can see all 8 LEDs, okay? So the red traces here are the front copper layer of the PCB, and the blue traces that you can see is the rear traces of the PCB, the copper trace that's connecting the pins together. I always start and try and get as much on the first layer as I can without crossing over, of course, because you can't cross over, and then only resort to the rear layer when I have to. And I've tried to retain that to just the ground connections where I can. It's not entirely possible, but it's worked out. It's there. All the connections are sound. And then if we go to the 3D view, you'll see what it's going to look like. There you go. That's what it will look like in the 3D domain, okay? There's your 8 LEDs, your 8 outputs, and the various jumper connectors for various things. These here are little screw terminals. Now the KiCad does not have a graphical image of those, but it's basically the same as we used on the prototype board. So one there, and then the eight outputs with the same kind of screw terminal outputs. The holes you can see, so first of all, these here are being lined up with the mounts for the PCB, the LCD board. So there will be pillar standoffs, just like the prototype, mounted here, here, and here. Then you get 3 good secure fixings to hold that LCD display on. These ones here, well, they are actually for some little plastic clip for the DIN rail mounts, so we can clip it onto a DIN rail in the rack. So it's nice and secure, it's not touching anything. So just have a look at that now. So this is what I mean by the DIN rail mounts here. This is like a plastic clip, and there's 2 retaining screws on either side here to hold that in place. So that will clip straight onto a DIN rail within the rack. They're sort of spring-loaded plastic, clip on, be nice and secure, and you haven't got to worry about it going anywhere. So that should work fine. So you can just see on here all of the circuit traces just over here. This is the front copper layer, traces here and here, connecting everything up. It's quite a laborious task actually to make sure you got every single pin connected up. When you look in this 2D view, you know, everything on here has to be exactly pin for pin connected correctly. Otherwise, it's just a whole waste of time and money doing it. The board will turn up and it basically won't work if you've got any one of these incorrect. So I've gone through every one of these pins and compared it with the prototype board using a continuity meter and buzzed each one out and basically ticked it off the schematic to ensure that it is correct. So there you go, I've gone through basically this board and I've put my test meter on, continuity test, pin for pin, and because obviously we know this works, so if that works and this matches it, then the PCB design should work. So I went through every single connection here and cross-checked, make sure that this matches this, and indeed it does, you can see. The only thing that I've changed here is that the output enable on these shift registers were driven by an inverting transistor circuit, but actually, because of these type of opto isolators that I ended up using, it doesn't actually serve any purpose. So I've done away with that, and I'm just tying the output enable basically to ground here. So that one and that one is basically tied to ground. So it's constantly enabled is. Okay, so to compensate for not having this output enable sort of mechanism, because the concern was that when you first power the board on, you don't know what the output state of these shift registers are going to be. It could be some random thing, so you don't know what these outputs are going to be set to. So I just put this warning note here that if the board is not powered or it's not in use, then you should basically isolate this jumper or remove the jumper or leave it on one leg. And effectively that means that all these outputs are not connected to anything because it's disconnected over here. And then you'll be absolutely fine. It won't trigger anything inadvertently. In addition to that, what I've done is the output that we did use for the output enable pin, the inverting transistor circuit, I've just now put an LED on there. So I will modify the software so that once the software is booted up and it's active, it will illuminate or blink this LED, so you know that it's now safe to reconnect this to whatever state you want, whether you want volt driven or volt free, and nothing will trigger unexpectedly. Okay. So in summary, I think this board is actually now good to go, and I think I'm going to now place the order. I've got to do a bit of work in some sort of design rule checks and creating the drill files, in other words, where to drill these holes, the Gerber file, which tells the manufacturer how to assemble it, how to manufacture it, and then I need to post all that off, go through their sort of check-in process, can take a couple of times, and get it ordered, and then in a week or so should get the board, we can try it out, and I will update you then.